Hey guys, welcome to Safi Mixed. In this video, I will let you know about a very necessary condition on the eigenvalue equation. So I first want to write down eigenvalue equation for an operator A. If A is an operator, then we write the eigenvalue equation in the form AFI equals lambda I kit phi sub I. We call this eigenvalue equation of operator A. Here, the kit phi I is in fact a set of functions. We call them eigenfunctions, and similarly, lambda I is a set of numbers. We call them eigenvalues. The eigenvalues could be positive or negative real, or could be complex. The nature of this obviously depends on the operator A. I have another video on the eigenvalue equation whose link I'll add to the description of this video. If you are interested in, you can watch that video as well, which explains other perspectives of the eigenvalue equation. So we are always interested to find the eigenvalues and eigenfunction of the operator, and if we could do that, we can then extract information about the dynamics of the particles which operator A corresponds to. To this end, we rewrite this equation in the form A minus lambda I times phi I equals 0. Here, this represents an identity matrix whose order is exactly equal to the order of operator A. I do this because lambda I represents a number and we cannot subtract a number from a matrix. Therefore, I multiplied the matrix with identity matrix. The identity matrix in matrix algebra is in fact behaving as a multiplicative identity, so we can multiply that with any number, and I construct a matrix. This is a matrix, that is the quantity inside the parenthesis is a matrix, and similarly on this side the 0 in fact represents a null matrix whose order is exactly equal to the order of matrix A. Now the important thing, or the purpose of this video, is to know about a very necessary condition on this matrix inside the parenthesis. And that necessary condition on this matrix is that the matrix inside the parenthesis has no inverse. And if it has no inverse, only then this equation has some physical interpretations. On the other hand, if the inverse of this matrix exists, the eigenvalue equation loses its importance to interpret certain behavior, physical behavior. For example, if the inverse of this matrix exists, then I would have a matrix like this: A minus lambda I multiplied with identity matrix raised to the power minus 1. And if I multiply this matrix from left to this one equation, I would then be able to write it in the form lambda sub I multiplied with identity matrix minus 1 into A minus lambda sub I multiplied with identity matrix, then the set of eigenfunction with kit I equals A minus lambda I multiplied with identity matrix and then multiplied with the null vector Z. So this thing, since this is a null matrix, therefore the result of this side is again a null matrix 0. That means nothing. And on this side, this is inverse of this matrix, and we know that the inverse multiplied with a matrix always results in identity matrix. That means the left side of this equation I can simply write like this: I phi I equals 0. Or in other words, I can just write phi I equals 0. So if the inverse of this matrix exists, that invalidates this one equation because the set of eigenfunction is 0. Or in other words, no eigenfunctions to this operator exists. So that means and particularly quantum mechanically, that means we cannot extract any information about the particle to which this operator corresponds. So to find the eigenfunction, the eigenvalues for a quantum mechanical system, this matrix inside the parenthesis must not have an inverse. And when that's the case, that is, this matrix has no inverse, then we know from our linear algebra that the determinant of such matrices, A minus lambda I multiplied with I, should always goes to 0. And that's what we solved. Then this is a set of equation whose number is equal to the order of matrix A, and then solving every equation leads to a number lambda I. So the procedure, the rest of the procedure I have already explained in my previous video, whose link I add to this to the description of this video. So you must keep in mind that the matrix inside the parenthesis for an eigenvalue equation has no inverse, and that leads us to set that matrix equal and that leads us to set the determinant of this matrix equal to 0, which then enables us to find the set of eigenvalues for the characteristic equation. Thanks for watching.